All right, what's going on, you guys? Another LeetCode video today. This one's called course schedule. So there are a total of num courses that we have to take, labeled from 0 to num courses minus 1. We're also given an array of prerequisites where there's basically going to be a bunch of pairs of prerequisites where the second value in the pair is going to be the prerequisite for the first value, right? So each course, by the way, it's important to state they're going to be represented by unique integers, right? So that's what we mean by those values. Each value is going to be a course, right? So and the prerequisites, right? That's basically all you have to understand there. Bunch of values for courses, and then the second value in the prerequisite pair is going to be the prerequisite for the first value. So, and they basically want us to determine whether or not it's possible to finish all of the courses. If it is, we return true. If not, we return false. So for the first example, we can see that there's only 2 courses, right? 1 and 0. And then we can see for the prerequisites, 0 is going to be a prerequisite for 1. That's fine. You can just take 0 and then take 1 and you're good to go. But what about the second example? So we have 2 courses again, 0 and 1. 0 again is going to be a prerequisite for 1, but 1 is going to be a prerequisite for 0. So we're going to have a cycle there, right? Because you cannot take 1 unless you've taken 0, but it's the same thing like vice versa. You can't take 0 if you haven't taken 1. So it's very clearly impossible, right? So basically, the way we're going to be solving this is a graph problem, right? So each course, right, each integer can be seen as a unique node or vertex in the graph. And then basically the prerequisites are like the edges of our graph. So let's construct this graph. So we're going to have a node for every course, right? So even if there's no prerequisites for it. So we'll have a 0. Technically, that we don't need nodes for islands because there's not possibly going to be a cycle on an island. But the graph can be disconnected, so we'll just build the whole thing. So we're gonna have a 0. There's gonna be a 1, all the way from 0 to 5, right? Because it's 0 indexed. So I have this 3 here. Let's see. 4, and then 5. Okay, hopefully these are in convenient locations for our edges. So the way we're going to direct our edges, right, is you have to take 0 before you can take course 1, right? That's the way that works in the problem statement. So we're going to have our edges going from the prerequisites to all of the next courses, right? So if you were to just take these courses chronologically, it's kind of how you can think of it, the way we're just going to set this up. So 0 is going to have an edge that points to 1, right? Let's see, 0 is also a prerequisite for 2, so we've got to have an edge going from 0 to 2. Let's see, 1 is a prerequisite for 3, so let's go around it that way. 3 is a prerequisite for 5. So we're just going over these one at a time. It's kind of how the code will work too. We'll just iterate through the prerequisites and add them like this. So 3 is a prerequisite for 5, 2 is a prerequisite for 3, and 1 is going to be 5 is going to be a prerequisite for 1. So let's just go around this way. That way none of those edges are intersecting. So basically we just need to do a depth first search to check for cycles, basically just at each node, right? So we can just start our depth first search. Also, well, before we start, we need a couple data structures, right? So we're going to need basically a way to keep track of nodes that we've already seen just globally. So the way this depth first search works is you only need to visit each node once, right? And that's like separate from the individual depth first searches, right? So we're going to have another data structure that keeps track of the courses or nodes we visited within a single depth first search, right? The path will determine whether or not there's a cycle. Visited will just keep track of the work we've already done, because basically once you've already visited a node within any depth first search, you don't need to revisit it at any point. So it's really helpful and necessary to mark each node as visited as we're traversing this graph in a depth first search. So yeah, so let's just start at 0. We'll go through these nodes 0 through 5. So marking them as visited and our path accordingly. So so this one is visited. It's going to be in our path. Okay, we need to do a depth first search, right, on its neighbors. So let's start the depth first search at 1. So this 1 is going to be visited, and it's going to be in the path. We need to continue the depth first search. So we can go to this 3, visited, and it's in the path. We're just making sure we're not seeing any nodes that have already been in the path, right? That's like the most important thing. Also, we're checking if it's visited, but yeah, anyways, okay, so continue the depth first search. So we have to go to the 5. So we mark it as visited, and it's in the path. Okay, and we're gonna keep doing our depth first search, but we see this 1, right, is in the path, right, is green, has been marked already. So we would return true within it from our cycle detection algorithm, right? I mean, it'd be false because it's impossible to complete all of them, but true in the sense that there is a cycle, because we're gonna have a separate check cycle function for the DFS, right? But anyways, a cycle has been detected here. So that in a nutshell is how you do the problem. If there were no cycle there, we wouldn't have to check any node that's been marked red. Does not have to be looked at again. But when we, if there were like no cycle here, like let's say this pointed to like a different node. Let's say it pointed to the 4. So yeah, let's say there were no cycle here. We'd mark this visited, it's in the path. Then we would start backtracking. We would leave the nodes as visited, but we would remove the green because they're no longer in the path when we're backtracking, right? Okay, so then you would start like a DFS on 1, or you'd try to, but you wouldn't be able to because it's already visited, right? So you would keep looking for nodes, right? 2 has not been visited, so we could start a DFS from there. So we would mark this as, visited, we'd say it's in the path, and then we would try to DFS. We'd see 3 has already been visited, so we're done now. So that's just the way that works. You only have to look at each node once. But anyways, yeah, I think in this example, there is no cycle. Yeah, but before there was a cycle. So that's kind of just 2 examples of a cycle and then not a cycle. So for the time and space, let's see. So the time complexity is going to be big O of vertices plus edges, right? So and the vertices, remember, are the num courses. Edges are that's dependent on how many prerequisites there are, right? So but that's the time complexity, right? Because in the worst case, you're traversing every vertex and every edge, right? So big O of V plus E for the time. And then for the space, it's going to be big O of V plus E also, because mostly that's going to be dominated by the recursive call stack. Because in a depth first search, in the worst case, you could, have to remember, or you can have a DFS that's as deep as there are, vertices and edges, right? In the worst case, not to mention we have 2 data structures here. But these are both going to be limited by the number of vertices, right? That's the most, and that's the largest these can be, is have the total number of vertices within them. So the space complexity is going to be dominated by big O of V plus E. So vertices and edges. So yeah, let's get into the code for this. So the first thing we need is just a data structure for the graph. I'm just going to use a hash map. So in C++, we get that O of 1 access hash map with unordered map. So we'll have an integer value and then a vector of integers for the neighbors, right? And the way this is going to work, remember just the direction of our edges. this integer is going to be like the prerequisite, and then these will be all of the subsequent courses. Okay, so let's build that graph first. So we're going to say for auto, you say take each prerequisite by reference. So for P and prerequisites, we need to basically just say we're going to push back the second value in the pair, right? So P1, because that's the prerequisite, and then we're going to push back all of its neighbors, right? All of the subsequent courses one at a time. So this subsequent course will just be the first value in that pair, so P is 0. Okay, so now the graph has been constructed. We also need those two data structures, right? I'll just do a, you could do an unordered set, but since since we know exactly how many courses there are, it's technically going to be more efficient to just do like a Boolean vector, right, for visited, because we can mark them, as visited just by true or false, and then we know exactly how many courses we're working with up front. So let's do it that way. Let's say we're going to have a vector of Booleans, and it's going to be, we'll say visited, and then it's going to be num courses size, and then each one will be false at first, right? Because they have not been visited. And then we're going to do the exact same thing for our path, right? We need to mark the courses that are in the current search path, right? So, okay, we need to now try looping over each node in the graph. So we'll just say for auto, we don't really care what the type is. It's going to be a key value. So for key value in graph, right, we're just going to take, we can say that the course is equal to kv.first, right? Okay, so we're looking at just that course, and we're going to say, we can have an if statement. We're going to say if not visited course. So if the course hasn't yet been visited, then we want to check for a cycle there. So we'll say check cycle. And we don't know what the parameters are going to be for that function, but that'll be our DFS function. And if there is a cycle there, then we can just return false, right? We're going to be returning true when there is a cycle. And if there is a cycle, that means we cannot complete all of the courses, so we return false. Otherwise, we can just return true if there are no cycles detected. So let's go ahead and implement that check cycle function. So let's do it as a private class method. It'll have a Boolean return value. So we'll say check cycle. We need an integer for the course that we're on. I'm just going to say C for short. We don't want to have to write out course a bunch of times, so because it'll get a little verbose. Let's get these data structures we need, right? So we need both of these. They're both going to be by reference. We also need the graph, and that's also going to be by reference, right? So we just have to change this syntax, right? We don't need the constructor. Obviously don't need the semicolons. And we can just comma separate them. And they're all going to be by reference too. Let's give us some more room here. They're all going to be by reference as well, right? Because we don't want to be making any deep copies, and we can treat them like they're global variables. So those will be by reference. So let's go ahead and seed this function for our DFSs before I forget, right? So we're going to be passing in course. We're going to be passing in visited, path, and graph. Okay, so at this point, the first thing we want to do, right, is check if this course already appeared in our path. Because if it has, we know 100% that there's a cycle, right? So we'll say if path C, right? So if it's in there, if that value is true, then we're going to return true. We know with certainty there's a cycle. Also, if we've already visited this node, then we can just return false because we've already checked that node. We know there's no cycle there. Yeah, so at this point, we want to set path and visited to true if they weren't already. So, path at C, just gonna set that flag to true. Same with visited, so visited at C, set that flag to true. Then we just need to iterate over all of the neighbors, right? And then continue the depth for search. So we'll say for auto we'll do get the neighbors by reference. So auto neighbor in graph C, right? That'll get all the neighbors from the graph, and just basically iterate through them. And we're gonna say if we need to check cycle, right? So we need to check cycle on neighbor, and then just pass in all of those other data structures. So visited, path, and then graph. Okay, and if there is a cycle, right? So if check cycle comes back as true, so if check cycle, we just return true. And that means there's a cycle there, right? Because we would have seen this would be true, right? And then that would result in this also being true. Okay. Otherwise, we're going to remove this course from the current path, right? So path C needs to be set to false because we're now backtracking, sort of, not really backtracking, but we're just like popping back up from the recursion. And while doing so, removing the course from this path, right? And then keeping it in visited though, and we need to return false, right, when we're done with all of this, because otherwise, if we never return true here, or if we never return true here, and we get all the way to the end of our search, it's just going to be false because there is no cycle. So yeah, this is pretty much all of the code. Let's try to, I'm going to remove some of these spaces because it's kind of hard to see all of it right now. But yeah, that's all of the code. So yeah, hopefully, let's actually make sure there's no bugs first. Perfect. Okay, yeah, hopefully this video helped you understand course schedule better. If it did, leave a like and subscribe, and I'll see you guys in the next video. Peace.